Hello, students. Today we are going to discuss center of gravity. Center of gravity. Some people call this one center of mass, but we are going to focus on center of gravity. First of all, I'd like to remind you how we balance a ruler in a laboratory. When we have a ruler in the laboratory, if we want to balance the ruler, we have to place our finger somewhere at the middle or at the middle. If the ruler is uniform density, uniform mass, then somewhere at the middle we can balance the ruler. So somewhere here, that's where we can balance the ruler. That's the background here. So it looks like the balancing point is here. And this balancing point is called the center of gravity. It is actually a point at which all the mass is thought to be concentrated. The point at which all the mass is thought to be concentrated. Think about a baseball bat. For a baseball bat, what looks like that. Usually it is bigger one side than the other. The baseball bat. This is a baseball bat. For this one, if you try to balance it, you will realize that the balancing cannot happen right on the middle, but the balancing has to happen somewhere closer to the larger masses, so somewhere here. So the balancing point is not at the geometric center of the baseball. It's somewhere there. You try it. If you have a baseball, try to balance it, and you realize that the balancing point is somewhere there. So our center of gravity is right there. So it's the center of gravity. Center of gravity. And here is our center of gravity. Center of gravity. Moving along, I might use an abbreviation. I just put center of gravity. That'll be the abbreviation. All right, what about the hammer? You know, you have a hammer somewhere, maybe. If you have a hammer, you might want to try to see where the balancing point is. And you realize that the handle is lighter than the metal part, then the balancing point will be somewhere here. So that's the balancing point of the, maybe somewhere here. So that will be the balancing point of the hammer. So hammer, that balancing point is actually what we call the center of gravity, the point at which all the mass is thought to be concentrated. Or we can define this as well, what we see is that in each of the three cases we had, the weight of each object, let me write this one. The weight of each object that I showed you, the weight of each object behaves as if it were concentrated. It behaves as if it were concentrated at a particular point. So it looks like the weight in each case behaves as if it were concentrated at a particular point. Okay. Now, as I said, we can think about the center of gravity. We can think about the center of gravity, that's the abbreviation, center of gravity, as a point at which all the weight of the object, or the weight, is thought, this is very important, is thought to be concentrated. Is thought to be concentrated. Now, the point is thought to be concentrated because sometimes you do not have actually a matter at a given point, but still the center of gravity can be still at the point where there is no matter at all. So that's why we are emphasizing that it's thought to be concentrated. So I have to expand why I'm saying it's thought. That's center of gravity of a hollow. Think about a hollow sphere, like a soccer ball. So hollow sphere, the center of gravity is at the what? Is at the center. Is at the geometric center where no matter exists. At the center, actually, there is no matter there where no matter exists. So that's why we emphasize that the center of gravity is a point at which all the weight or mass is thought to be concentrated. And for the objects we have seen here, well, in each and every case here, there is actually matter available there. There's some matter at the point where we are balancing, but it doesn't have to be the case. The center of gravity can be at a point whereby there is no matter at all, as we can see for a hollow sphere. The center of gravity is right at the center where there's no matter at all, no mass at all. All right. Okay, so it is a point where all mass is thought to be concentrated. That's the point. Now, there are some interesting features of the center of gravity. I'd like to share with you two interesting points about the center of gravity or observations that we see. Number one, it has to do with what we do when we have a wrench. You know, I talked about a wrench in one of the PowerPoints. It's a tool that we use to, turn a stubborn board, for example. If you have a wrench like this one, and maybe for some reasons, maybe the center of gravity is here, and you try to toss it on a frictionless surface, allow it to move on a frictionless surface. Make sure that it spins along the way, and it slides across. So we see something very interesting that when this happens, and we focus, let's say we paint red. Okay, let's say we paint red on the center of gravity of the wrench. So let me paint red there, paint red there as a center of gravity. Now we toss it, so it spins as it goes on a flat surface. One thing that is very interesting that experiments show us is that we see that if we focus our eyes on the red dot, we see that the red dot behaves as if it's just translational motion. So the red dot will actually exemplify translational motion. So this is what is observed. If the surface is frictionless, then the motion is steady, and therefore the center of gravity behaves as if it's in translational motion, whilst every part of the other wrench will be spinning around the center of gravity. So this is just a focus, just focusing on the red dot. This is what observations tell us. It's very interesting. The wrench is spinning, but your eye is focusing on the red dot, and you take a snapshot. This is what we see. So it's very interesting. It looks like indeed the center of gravity can be defined as a point at which all mass is thought to be concentrated. And its behavior exemplifies translational motion, just like the motion we have seen before, a translational motion. Yeah, it's very interesting. And second observation about the wrench, if we toss it into the air, allow it to follow a parabolic motion, try to spin it as you toss it, well, it will be spinning. But one thing that is observed is that the red dot, if you focus your eyes on the red dot, will actually follow a trajectory like this. I don't want to draw all the dots, but I want to show you that this is what will be the pattern. I don't want to confuse you about the dots because the dots will follow a certain pattern. that we can describe later when we talk about projectile motion. But for now, I just want to tell you that if you toss the wrench into the air, if you toss it into the air, that's what you're going to see. If your eyes are focusing on the red dot, toss the wrench into air. This is the kind of path you should be able to see, the kind of path. Again, I want to draw all the dots because there is a special pattern that they follow for any projectile. There's a special pattern that dots will follow. We'll discuss that later. And this is a toss. Is case number one. As I said, the wrench is tossed on a flat table, which is frictionless. And this is what we see. We see that the motion is actually translational and linear straight line motion. This one is also translational motion. This is also translational, but parabolic motion. So that's the behavior of the center of mass. It's very interesting. Now, I would like to close the discussion here, our brief discussion, by looking at what we call stability. Stability. Why is it important for us to learn about center of gravity? Well, it is important for engineers, building designers to think about how to erect buildings that are stable, right? So there is a rule for stability for anyone who is designing buildings, they have to think about. So the rule has to do with the position of the center of gravity with respect to the base of the structure. Assuming that we have a structure like this one, which is actually similar to the Leaning Tower of Pisa. So you might have heard about the leaning, sorry. This will be Leaning Tower of Pisa in Italy. It's a long tower that actually seems like it's about to fall, but it doesn't fall for so many years. Now, the center of gravity is somewhere here. Now, the rule for stability tells us that if you draw a line from the center of gravity, remember center of gravity, the symbol is this. If you draw a line straight down, the line must pass through the base of the structure. So our base is actually here. That's the base of the structure, and the line passes through here. According to the rule for stability, then this building will be stable. So this was what we call stable equilibrium. Stable equilibrium. And the rule is simple. Just draw a line from the center of gravity, and the line has to be straight down. If it passes within the base, if it falls within the base here, inside the base of the object, then the object is in stable equilibrium. It will balance, so the object will balance, so it will balance. So it will balance, and that's what we see here, it will balance. And that's what we want as engineers. We want structures to balance, to be in stable equilibrium. Now, if for some reasons, your center of gravity, the way you construct the building, if you, for some reasons, you draw let's have a building here, and you want to try to design a fancy building, and you find yourself having this upper side more massive than the bottom, and the center of gravity happens to be up, and you try to draw your line. I'm trying to make the line so it passes outside. So if you draw the line, yep, in that case, if you make the top part so massive such that the center of gravity is located there, you see that the line that you draw towards the bottom pass is just out. It's out. In this case, you have a problem. It produces a torque. So this force you see here will produce a torque, produces a torque or a turning effect. Remember, torque is a turning effect. And this torque will actually topple the tower. So it will topple the tower. The top topples the tower. So the tower won't be, it won't achieve balance. It will fall down. It topples the tower. All right. So it is very, very important to consider this simple rule. So very, very simple rule. So maybe let me write it. I just mentioned the rule, but it's better to put it in writing here. So the rule for stability. If we draw a line straight, if you draw a line straight, if we draw a line from center of gravity, downwards, and the line falls inside the base, of the object, the object is in stable equilibrium. So the object will balance. Otherwise, it will topple. Okay, so that's it. So otherwise, if this is not the case, if your line does not fall inside, then the object will topple. All right, anyway, I will stop here. In this lesson, we discussed the center of gravity as the balancing point. We have seen that it depends on how the mass is distributed in the object. It can be at the geometric center, or it can be somewhere towards the massive object. The center of gravity can be thought of as a point at which all the weight is thought to be concentrated. And for that reason, because it's just a thought, it is actually a point that can be at a site where there is no matter, just like a soccer ball, just like a sphere, a hollow sphere. And we have looked at important points about what happens when we spin a wrench on a flat surface. When we spin a wrench on a flat frictionless surface, our focus being on the center of gravity, we see that the center of gravity behaves as if all the mass is concentrated on that point. And then we can see that we can observe translational motion in a straight line, steady speed motion. If we toss the wrench into the air and then the wrench spins, we can focus on the motion, and then we see that the motion is also parabolic, it's translational. And this is very interesting because it looks like the center of mass demonstrates translational motion, whilst the other parts demonstrate rotational motion. Right. We talked about stability. Stability is very, very important for building structures. The rule is very simple. Draw a line from the center of gravity down straight to the bottom. If it passes through the base of the building, that's stable. The building will be stable. Otherwise, the center of gravity produces a force, and that force will actually produce a torque, and the torque is the one that will topple the building, the tower. All right, I'll stop here. If you have any questions, please let me know. Bye for now.